see cluster methods that were less successful. But that's really about the selection of characteristics that you use to build those clusters.
Yeah, like the common tracking study.
I've seen others, especially, but yeah. How do we know that the sample is okay? I mean, of course, sometimes, as in this case, you can compare your sample characteristics to some official statistics, which is really nice if you're able to do that. However, we don't know everything from official statistics. So indeed, you guys could compare your sample to official gender distributions, official religious denomination distribution, things like that. You couldn't compare your sample to official data about the emotional state of people, because those official characteristics don't exist, and you assume that you still have a good sample because it looks good. But there's also mathematical approach to assessing whether, with some likelihood, our sample is a good sample based on the central limit theorem. What is important before we go into that? It's very interesting. You know, whenever you see polls that claim representativeness by commercial companies, these are around 800 to 1,000 people. That's the same for the United States with 240 million inhabitants, as it is for Austria with 8 million inhabitants, as it is for Luxembourg with 300,000 inhabitants. So the ideal sample size, in the end, does very little depend on the size of the population for a truly random sample. And again, while it is the case, would be based on assumptions formed from the sample limit theorem. How do you pronounce this? So the random sample, and again, we speak about the simple random sample here, because that most easily explains what happens here. Is drawn from a population, then when the sample is sufficiently large, the sampling distribution x will be approximately normal. I'll show you in a second. Let's keep this mathematic for a second. When n, again, the sample is sufficiently large, the sample mean will approach the population mean. So that's what we want to reach in the end. That the characteristic of the sample, in this case the mean, is equal or at least approaching the mean of the population. So you see, when it's sufficiently large, concluding that, yeah, indeed, the larger the sample size, the better our estimates about the population based on the sample tend to get. This is coin tosses. You know, you've got a coin, you toss a coin. There's an equal random chance every time you toss the coin again that it's landing on head or tail. Yeah? And this is the number of cost coins. So the mean of cost coins, let's assume the tail is a 0 and the head is a 1, should be 0.5, right? That's the exact middle of the 0 and the 1. That's the mean. And what we see in this graph is the more often you toss the coin, the closer the true values, which is the black line, come to the hypothetical value, or the mathematical value, which is the red line, 0.5. So I toss the coin the first time, it lands on, what did I say? Head, 1. Yeah? I toss it the second time, it lands on tail, but that doesn't mean I'm going down to 0, because I already first tossed, you know? So I had a 1 plus a 0, taking the mean of a 1 and a 0. That's probably the third toss already. So and the more often you toss the coin, the more the true values, the mean values of all those coin tosses will come to the red line. The bigger the sample, yeah, which each additional sample in this case, sampling point, the data quality becomes better because it's closer to the true, and the 0.5 is the true distribution in the population. This is very similar picture, it seems, but this is based on a mathematical function that tries to figure out what the relationship is between the size of a sample and the theoretical mean of the sample. And here you see, you start with 0, and there's big variance here, right? So very small samples don't usually get very close to the true. But as soon as you reach, this would be 1,000 approximately, it already looks quite decent. Actually, already start looking quite decent from 500 onwards. And then you see why many commercial polling firms do samples of 1,000 and not more, because there's not a whole lot happening between 1,000 and say 4,000 or 4,500. Once you get bigger than 4,500, say about 6,000, then it's ideal. Then the true random sample really turns out exactly the population characteristics. But between here and here, there's a lot of costs involved for most commercial polling firms, but also for most academic polling, for most academic surveys. So we rather accept, on average, some deviation from the true mean. We can deal with this and calculate this to some degree, rather than spending much more money to have a sample which is maybe coming still closer. This is a different characterization of this, but so this is the true distribution of the population. This is the sampling rate, and you see, and we'll come to that difference in a second. The more often you draw a sample, the closer that comes to the picture. This is all of this, or much of it. All of this is based on assumptions from the normal distribution. We all know the normal distribution. I guess many characteristics in this world out there are interestingly normally distributed. This is the IQ score of people. This is the height of women, the height of men. This is the weight of people. I think this weight something. Can't remember. But there's endless of these. If you start googling this, you can get 1,000 of these pictures of normal distributions that are out there. Now the very cool thing is that the outcomes of sampling procedures also distribute normally. So, you always look at the mean in your sample. That's what you're interested in, because that would be the statistic that would be the characterized distribution of the same thing in your population. The more often you draw a sample, the closer this mean, and the closer this mean value you get from the sample is to the true population mean. This is the true population mean. This is what we aim to achieve. If we just draw a small sample once, it could be, we could end up here or we could end up here. The more often we draw the samples and the bigger the samples get, we get to the point that we can be fairly certain that we're coming close at least to the population mean. So these things also show the characteristics of the normal distribution, which is very handy for us, because then we can do some estimates based on that. I'm going to skip this. I'm probably going to skip this. Have a look at this. It's the same story, you know. bigger sample sizes, more samples, getting closer to the true mean. Here there's still a good likelihood that you're quite far off. Here the lies. Now, when we read about polls in the papers, for instance, and around election times, we often get reported something which is called the margin of error. So we always assume a true random sample. The mean of the true random sample is very close to the real mean, but we also estimate that yes, there is a chance that it's slightly off. Again, sorry for flipping back and forth here. Again, even if it's here, it could be here or here. Right? And you need to have really big samples, as we saw in the previous graph, going to 6,000 or more maybe, that this becomes a very, very tiny peak, and we can be very sure that we land on the true mean. So what we then try to do is estimating how far our sample mean is off the real mean. And we do that based on standard errors, which is the average deviation of the estimated mean in the sample from the true unknown mean. And that standard error depends on the size of the sample and the variance in the population of what we're looking at. So the bigger the sample, the smaller the standard error is, but also the smaller the variance in the population of what we intend to measure, the smaller the standard error becomes. And this is then often what we get when we draw different sample sizes, again, true random samples from populations. So if you draw a sample size of 96, and again, if you're interested in mathematics behind, sorry, I try to, in these courses where it's about introduction, I try to avoid formulas and too much mathematics because I have the impression that it scares people away. But if you're interested in the mathematics behind this, it's a simple Wikipedia, Google search. I can send you some articles or something, anything. Email me if you're interested in getting the mathematics behind this. But it's not rocket science. It's fairly easy. And you know, it's very easy. So sample size 96 means we're dealing with a margin of error of 10%. So our mean value that we have in the sample might be actually 10% lower or higher in the true population, because we've got a very small sample, right? So let's look at, this is what we have in survey research, right? With a sample of 1,000 something, roughly 1,000 people. Margin of error reduces on average to roughly 3%. No, it's 4% with 600. That's why, especially in Austria, where the polling firms don't have much money, they tend to rely on 600 samples because they claim that's enough. We can deal with this. But if you get lower, the margin of error really gets worrisome to some degree. And again, if you increase this, the margin of error will also decrease again. But we quickly have to add much more sample size to really get this.
Is it the acceptable
margin of error?
What is the acceptable?
Depends on what you want to do. I'm very often frustrated when I look at poll reporting in news media. I don't know what it's like here, but in Germany we would get the Social Democrats lost a percentage point and the Christian Democrats won a percentage point. And it's all in the margin of error, right? But it's becoming a big story. They're going apart. They're deviating from each other all of a sudden. Or when it's very close races, one is a percentage point in front of the other. But he's still leading. No, he's not leading. It's all within the margin of error. We don't know. It's basically the same thing. So if you're interested in such type of predictions, smaller margins of error might be might be nice, but in science we usually deal with 95% accuracy.
What about newspapers? If you take newspapers which are with your 4 number, or you take movies for instance, you take 10 movies for study, how do you
Don't. With a sample of 10, don't think about margins of errors. It doesn't make sense. If you take 5 newspapers and you want to claim something about all newspapers, tricky. But if you say about those 5 newspapers and I look at a year of coverage and I sample somewhat randomly my articles within that year of coverage, you can say a lot, and you will probably end up analyzing 200, 300, 400 news articles, and that would allow you to say a lot about the general coverage in that newspaper. Again, with some margin of error. Just very briefly, some problems of random samples. Of random sampling. The population is unknown. I can only draw a random sample if I know what the population is. I can only draw a random sample of 20 of you here in the room if I know how many are here, if I've got your names, or at least can assign numbers to you or whatever, and then I can draw random samples. You know, if I would be standing here alone in the room and I would be told to draw a random sample of 20 of this class, I would have a very hard time. I'm still not sure I could do now because I'm not sure whether everyone who registered is actually here. So, what is the population? Do I know the population? There's a problem that we deal with. Then, and again we'll come a bit more to that tomorrow, to response rates, but I cannot reach the elements in my population. So I sample newspaper days of coverage that I want to look at, but those are not available in the library. Someone stole the page. Read it from the archive. People don't pick up the phone. Well, actually, we sampled someone, but we don't get his phone number, or a phone number in this case. They're not at home. You know, you ring on their doorbell, but not there. Happens all the time. Very annoying, happens all the time. And then you call someone or you ring on the door and they actually answer the phone or they open the door but they don't want to participate. Doesn't happen with newspaper articles. Also happens very often. Again, telephone surveys in the European contracts nowadays, 30% response rate. If at all. Face-to-face, not much better.
Questionnaire? You submit a questionnaire?
Postal surveys are horrible in terms of response rates, 10%. Online getting better. Online getting much easier.
Why everyone put assume yours? Everyone should be yours.
In Europe, there is in countries that have an internet penetration of say above 90-95%, which is the case for most Western European countries at least, there's an increasing move towards online service.
Are you going to talk about any
I don't look at results, but we'll compare what the advantages and disadvantages are tomorrow when we talk about service. But there's increasing use of online service. There's also big hesitance to do that because we still get a bias, you know. Even if with an internet penetration rate of 90%, we know that there's a tendency that older people, even if they have an internet connection, might not be on their computer very often and on the web very often, and that lower educated people do tend to fall out of those samples. Now, it's an interesting discussion. Maybe we'll do more of that tomorrow, but it's an interesting discussion because between the old school elected survey researchers and maybe a bit of a younger generation. And you know, there's still this idea that face-to-face is the gold standard, and maybe face-to-face is the gold standard indeed, because that gives you fairly decent response rates and a good way of doing selection. but telephone, most of the traditional people would still prefer telephone. I'm very skeptical about telephone. You know, I don't have a, what's it called? I only have a mobile phone with no landline, exactly. But mobile phone numbers are no register. Only landlines are registers.
Yeah.
So how can I do a random selection of phone users only using landline numbers? Not very convincing. And that adds to, and there's a bias in there. So we know that younger people in Europe, ethnic minorities, don't have landlines much more often than other people. So you get a structural bias into these things as well, and then adding to response rates of 30% for telephone. I don't think online is doing much worse actually in these contexts. We talked about online in India yesterday, and of course the context here is very different. So online would give you a much more biased type of sample.
That's changing very fast.
Let's see what happens. Is it fast? I don't know. I do this tomorrow because we want a bit of time for the tutorial, and I talked longer than I should have anyway this morning. So what we'll do is take a quick. We'll start with this tutorial, which means we split up in groups again. When you feel you're done discussing, we'll have a break, I think, and then we have a break now. Oh, sorry, we have a break now, and maybe continue at 11:30ish, 11:35 or so, and I'll say something about what I want you to do in the groups. That's fine. Yeah. And maybe points to add to what we talked before. One is the fact that sampling in India is a bit more complicated really relates to the fact that, and we saw that on one of the slides, that the variance of characteristics that we are interested in is very large. So on a lot of demographic, other characteristics, there's a lot of variance within the country, which causes sample sizes to be bigger than usually to take care of that variation. We saw on the one slide, the bigger the variation, the bigger the sample needs to be basically to cover that variation. The other point is, sorry that we got stuck a little bit with elections. When it comes to sampling, we often very quickly talk about survey research, and I try to add a few content analysis examples here and there. But we very quickly come to survey research, and when we talk about survey research, we, from certain perspectives, very quickly end up with election surveys for some reason or the other. So apologies for that we got a bit narrow in terms of topics that we talked about. Tutorial. I'd like you to sit in the same groups as yesterday. I hope you remember your questions and what we talked about yesterday. And basically, in light of the research question that you now more or less formulated, I hope, what would be a most appropriate sampling strategy? And maybe, try to take into account some pragmatics here as well. Like, you could dream up the world now, but we all know that samples of 50,000 people of a population, or sampling 10 years of newspaper coverage for manual analysis is going to be very tricky. So try to reflect a little bit on pragmatic issues here as well. So what would be your most appropriate sampling strategy? Motivate that choice. Discuss why you would do the one thing and not the other thing, whether there's advantages or disadvantages to certain sampling strategies that we talked about. Consider if the population is known, for instance. That's a very simple consideration, but something you can and should maybe take into account. Do you need a random sample at all? And if you don't need a random sample, why do you not need a random sample and get away with a non-random sample? What's the purpose of your research question, and is randomization essential to answer that research question or not? And then discuss what types of generalizations you're likely to be able to draw on your sample, based on your sample. Again, generalization sounds like randomness. Do non-probabilistic, non-random samples. Can you generalize at all? And, these things could be taken into consideration. At least that's stuff I want you to discuss. Because there might be, maybe you have a convincing argument that with a certain non-random sampling strategy you can still say something about a somewhat bigger number of cases than that in your sample. So consider these things and try to discuss these things. Again, would be great if for the final presentation on Friday you have maybe 2 slides, 3 slides in your presentation that cover the discussions that you have about these topics and maybe your decisions that you took and the motivations behind those decisions. That would be the outcome of, say, the next roughly half an hour, because that's the time we have left after a long break and been talking for a bit too much. That would be great. Again, split up in groups. I'll walk around the room and try to get some sensible stuff.
Visualization only means what objects we find the mean or result.
No, what generalizations in terms of, can you say based on this population a bigger number of cases? Can you generalize from the results of your sample to a wider population? Yeah?